Alright, in this video we're going to finish the lecture about transformations, and we're going to start with the idea of how to simultaneously transform or think about transforming many variables as a set or all at once. And so we're going to start thinking about multivariate data, and of course the graphical display for multivariate data is a scatterplot matrix, and primarily we're going to be worrying about the predictor variables. Probably more, we're going to be worrying about them a lot, and probably more than you would think we should. It's going to turn out that much of our statistical life and data analysis success is going to depend on how the predictor variables are handled, and I think it's a little bit surprising about how important that handling is. So in the second bullet we mentioned that building good regression models, we're going to want to have predictors that are related to each other in a linear fashion, and that means that we have upward trending or downward trending patterns. No pattern is also fine. It's just curves and obvious curves that are going to cause us a lot of trouble understanding and interpreting our models. So one thing to know is that if the mean function, in the third bullet here, that if the mean function of y as a function of the predictors can be expressed as a function of this linear combination of the betas multiplying the predictors, then having linearly related predictors are going to let us be able to estimate the beta parameters well without really needing to know the g function that controls how the linear combination beta transpose x becomes the mean function. We won't need to really worry that much about the little g function because it will come to us quite easily if the predictors are linearly related to each other. That is an upcoming attraction. And so here we get at quite a bit of a theoretical result, but it's going to have important implications for our lives going forward making models. And it's called the one-dimensional, the 1D estimation result. And so what I'm talking about here is that there is the quantity A, capital A, which is related to a linear combination of our predictor variables. And so by the matrix X, I'm talking about our matrix of predictor information. And there's another quantity B, capital B, which is also a linear combination of our predictor variables. And so suppose that on average the value of capital A given information about B is a linear function, an intercept plus a slope times B. If we can relate A to B in such a fashion, if the predictor set X are linear predictors, then this kind of linear relationship holds no matter what quantity A and B are. For any of those linear combinations, anything we could construct, the A quantity and the B quantity are related to each other by a linear function. And that's if the predictors interrelate to each other in a linear fashion. That is what we refer to right here as the predictor set X being linear predictors. Well, if we do have linear predictors X, then when we estimate a parameter vector beta to produce an estimate beta hat, it turns out that that will be a consistent and very good estimator, even if we don't know the exact way that the predictors relate and form the mean function that I talked about on the previous slide, the little function g. We'd be able to estimate that little function g from just a two-dimensional scatter plot of y versus the predictors. And that's going to be an important plot later, is that if we have linearly related predictors, we can figure out what the little function g is just by plotting y against the predicted values. and that would accurately reveal how the mean function works. On overhead 19, we're going to think about a set of predictors, and we might be interested in simultaneously transforming them to be more multivariate normal and have joint normality, which is a special version of linear predictors. So if we had a bunch of predictors x1 to xk, we might want to think about what lambda transformation vector lambda 1, lambda 2, lambda 3 up to lambda k would produce a set of predictor variables that are the most normal or jointly normal. And so what we can do is there are techniques within the R software system that we can find what transformation vector lambda is the best one, and we can also do things like test whether that transformation vector lambda is significantly different than some hypothesized vector lambda naught. And we'll be able to tell whether we have data evidence against such a hypothesis. Here would be an example. I've got some highway data for states in the United States, and we'll create a scatterplot matrix of the tax rate on gasoline, the length of roads in the state. I forget what ADT is. I forget what these other aspects are of these roads. But you can see we have a scatterplot matrix. And some of these plots are really quite, blobby, not really too much of a pattern going on. Like here, TRKS with shoulder is a little bit of an upward trending pattern, but very weak. But a plot like SIGS1 against TRKS shows a really clear nonlinear curved pattern. And so that would be visual evidence that this set of variables is not linearly related. What could we do to produce a more jointly normal set of predictors? Well, on overhead 21, we show the same basic scatterplot matrix command, except we give it the option of transform equals true, and we tell it to do the Box-Cox power family, and it goes through and it estimates the best it can what parameters lambda should be used for these things. And you'll notice length, the best transform is to do a transform of 0 or logs. Same for ADT, TRKS. Shoulder, it decides it should do nothing. That's a lambda of 1. For SIGS1, it looks like it should log it. And this would be a way to simultaneously transform this set of predictors the best we can. And you'll notice that we don't have really big curved scatter plots anymore. Some of them are quite blobby with no real apparent pattern, but that's okay. We just want to avoid really bad curved patterns. Here is the output from such a command. We can ask for printed output for such things, and so we select the power transform command, and we tell the power transform command the set of predictors that we want to use. We want to use a binding together of the set of length ADT, TRKS, shoulder, SIGS1, and then we want to have that not related to anything else. We just want to transform that set. So we have as a function of nothing, or of a column of ones, and we produce an output object answer, and so then we give a summary of that output object answer, and right here in the first column we get the best maximum likelihood estimates for each of the lambdas that are selected for each of these variables. And then we get upper and lower boundaries, sort of a confidence interval for the suggested lambdas. And we can look through these confidence intervals and see if we can find any reasonably coherent choices. So for example, for length, you can see that an obvious choice here might be a value of lambda of 0, since 0 is in this interval. We can also see that it's sort of on the border of square root, lambda of a half being reasonable. These confidence bounds give us guidance about what might be reasonable lambda choices. Remember, we never will particularly use these best estimates. We'll use these best estimates as a guide to produce a standard kind of power transform. There's some tests that come out as part of this output. Down in the bottom we get 3 lines of tests. One test we might want to be interested in testing is whether every variable should be transformed like a log. That's what all of these lambdas being 0 means, that every one of these variables should be transformed to be a log. We get the test statistic, likelihood ratio test, we get a p-value, and so we see very clear evidence to rule out a null hypothesis like doing all logs. The second test here, you can see the hypothesized lambda vector, lambda naught, is to do nothing to all the variables. Every variable should be transformed to the power 1, in other words, do nothing. And from this test statistic and this very small p-value, we see we have lots of evidence to rule out a null hypothesis like we should do nothing. So very clear evidence to reject that hypothesis and support the alternative that we should do something for transforming these variables. The third line is a proposed transform vector that does log of all of them except for shoulder, or SHLD, and you can see that that hypothesized vector is not rejected, and that might be a plausible way to proceed. And I guess that is all that's being done here, just comments that I just explained about that output. You can also specify a specific test to be performed. So after you do a power transform command and all of the lambda information is stored in the object ANS, or answer, you can test a particular transform vector using the test transform command in the car library, put in the power transform object ANS, and then supply a lambda transform vector. And you'll notice it does the test, it does a likelihood ratio test statistic, and p-value. You will have seen that one before as part of the standard output. But I just wanted to show you the test transform command could be used to test a particular vector that you would specify. Remember that each one of these spaces corresponds to the predictors in the order in which they are specified in the power transform command. And so on slide 25, I go through a test in a formal way about how you would test a particular lambda vector. This is how you will perform tests on exams and on your homework when you're testing transforms. So please read through overhead 25 so you can see how to phrase your answers, how to phrase the conclusions. In this case, we don't have any real evidence to rule out a lambda vector like the one proposed. And then in the conclusion, you'll see I explain what that lambda vector would be interpreted like. We finally get to the problem of trying to transform the response variable. Sometimes we have our predictors linearly related, and we've done the best we can on our predictor matrix, but the mean function of a transformed version of y as a function of x might be linear. If we could just figure out the right transform t of y, we could do a nice linear regression model, multiple regression or simple regression. And it turns out that there are some very nice techniques for figuring out what the correct transform t of y will be. And it turns out that the thing to do is to plot The fitted values, y hat, in the fourth bullet here I mentioned that the way to figure out the right t-transform is to plot the fitted values, the predicted values, the y hats, from a regression model and plot them on vertical and have the actual value of y on the horizontal axis. It turns out that the shape of that plot is in fact the shape of the function t that is needed to get a linear model. And so this is what we're going to be doing. And we can also do this for many different kinds of transforms lambda, and we could plot several versions of this, having the fitted values on vertical and have the y values on horizontal for a variety of choices for a parameter lambda, and we could figure out which one most closely matches the function t of y. So we'll put a bunch of candidates on the same plot and look for the candidate lambda that produces the closest pattern. Here's an example for doing that. We have a basic model here, M2, that relates the tax rate for gasoline in a bunch of states, and we'll explain it as a function of characteristics of the roads in particular states. So we have a basic multiple regression model, and we can use the inverse response plot to find an appropriate transform to transform the rate variable so that a linear multiple regression model will be appropriate. Right now it might not be a terribly good choice because rate might not be in a very good measurement scale. Can we improve or transform the rate variable to make our modeling better? Well, we use the inverse response plot command. We supply it with an input of an estimated model, M2, which was defined right back here on overhead 28. M2 is a regression model. And we look through the lambda choices of inverse, log, square root, and do nothing. And we are looking for residual sums of squares that are as small as possible. And you can see that for inverse, the residual sums of squares are quite big. For doing nothing, lambda of 1, they're quite big, but they get smaller right around logarithm or square root. And so when we look at the inverse response plot, remember the predicted values from a variety of model, the predicted values from a basic model are on the vertical axis. This would be the y hats from M2, and we have the response variable rate on horizontal, and you'll notice we have a curved band of points suggesting some kind of transform is probably needed. According to the inverse response plot, the best suggestion is a lambda of 0.18, which is very close to something like a log. And it is not surprising that the black curve for these points is very close to the green curve. You notice black and green are almost indistinguishable, suggesting that something like the green or a log transformation would be a good choice, as is mentioned here on overhead 30. Another technique for deciding on a transform of the y variable, the response, is the Box-Cox method. And it is the Box-Cox function. You give it a basic model, estimated model input, M2, and it plots a likelihood curve and a 95% set of confidence bounds on the lambda scale for what values of lambda produce residuals that are the most normally distributed. So notice that the Box-Cox method is designed to catch and induce normality and bell-shaped patterns in the residuals. It is not, I repeat, it is not designed to fix curved mean functions. It is designed for a different purpose to achieve normality. Now, often those two things go together, but not necessarily. You will notice that from this particular method, the suggested transform is around a logarithm as well. The reason I say that is because the confidence bounds contain the value of lambda 0, which is a logarithm. You'll notice that this likelihood function is a maximum right around the logarithm as well. Sometimes you can have response variables that are both positive and negative. And if you have non-positive values for a variable, it is hard to do some of the power transforms like a logarithm, because you really can't take a log of a negative value. So what we do is something that's called the Yeo-Johnson family, and it separates out the values of the variable that are negative and does a separate transform on the negative values, and it separates out the positive values and has a separate lambda transform for those. And that is an option on many of our commands to specify a Yeo-Johnson family for our commands. I'm not going to stress this, but I just want to point out that taking transforms of variables is sometimes difficult if there are negative values or zeros. You can't take the logarithm of a 0 or a reciprocal of a 0 either. So a lot of times you'll have to do some sort of modification either to the data by adding 1 or by doing some sort of transform family like this one on overhead 32. Our final overhead sort of gives you a preview about how we're going to do modeling work. One of the first things we're going to be doing is by taking care of our predictor variables first, modifying them, transforming them to remove obvious nonlinearities and curvatures in their pairwise scatter plots. And then once that's taken care of, we might start worrying about the response variable through the inverse response plot or a Box-Cox choice. And then we would be analyzing our models on the transformed scale. I hope this is helpful.